Hello everyone. Today I will introduce the G-High APM32F4xx DAL SDK. This introduction mainly consists of the following parts. The first part is overview of the SDK, which includes the overall architecture, SDK composition, supported devices, file directory structure, and introduction to each part of the SDK. Then is SDK Quick Start, which includes how to run routines, how to develop DAL application, and how to develop DDL application. It can be seen from the architecture diagram of APM32F4xx DL SDK that there are several layers from hardware to application, including hardware, device abstraction layer, device driver layer, board support package, middleware, and application layer. It can be seen from the DAL SDK application composition that its application layer includes routines and template engineering. The middleware includes USB, RTOS, file system, and network protocol stack. The IDE support includes Kel MDK, IAR, and Eclipse GCC. The drivers and components include DAL libraries, DDL libraries, CMSES core device files, BSP, and some component drivers. The suitable MCU in SDK includes F405, F407, F417, F465, and F411. The suitable compilers include AC5, AC6, IAR, and GCC. The optimization level of the compiler is the highest optimization level of each compiler. AC5 is level 3, and AC6 is also level 3. The directory structure of the entire SDK is shown below, including onboard support package, component driver, development board routines, DAL library and DDL library, device header file, startup file, and connection file. In addition, it also includes some commonly used middleware, such as USB library, file systems, RTOS, and network protocol stack. It also includes Keli DFP package. You can see the introduction to the content of the entire SDK in the README file of SDK. Next, we will introduce the DAL library in the SDK. DAL provides a hardware interface function for underlying driver and application interaction, and it provides a universal, multi-instance, and function-oriented API with high portability. For example, in UART peripherals, the DAL provides the API of initialization and control processes, process for management of UART polling of data transmission and receiving, process for management of interrupt of data transmission and receiving, and process for management of DMA data transmission and receiving. DAL also provides two types of API. One type is General API, which is general throughout the entire MCU series. The other type is Extended API, which is only available for certain specific MCU models. This type of API has an X suffix. We can see from the table below which API is included in the general driver file and which API is included in the specific driver file. The driver file of the entire DAL consists of the following files: APM32F4xx DAL H files. These two files are used for initializing the DAL library, which includes a SysTick interface delay function and dbgmcu and remapping function. There is also a file with the def.h suffix, which contains common resource files in the DAL library, such as compiler adaptive macro, enumeration, and structural body. There is also a log, and it provides a lightweight logging component, which includes some functions of system-level log printing and setting of log printing function. Another type is the file with the suffix of chas.ppc.h, and it is a general peripheral driver file, including all general API of APM32 device, such as DAL ADC.c and UART.c. In addition to the general module driver files, there are also files that end with the suffix of eppx.ch. This type of file is the Extended Peripheral Module Driver file, which includes the specific API of specific model or series, such as the files ending with the suffix of ADCX or FlashX. Besides, there is a file ending with device CFGG template. This file is a template file, which includes a set function file with all initialization functions of DAL library initialization, clock initialization, and GPIO initialization in the application. Users can copy this file into their own application to carry out a series of initialization work. There is another important file, namely DAL CFG template file. This file is the configuration file of the entire DAL library, and users can customize the configuration of functions for the entire DAL library. Users can also copy this template file to their own application engineering, delete the template suffix, and use it as the configuration file of the entire DAL. There is a description about the files just introduced in the following picture. The following picture shows the file inclusion model of DAL library. It contains the file types of the underlying configuration register file on the far right of the picture, the driver layer file to the left, and the configuration file of the entire DAL library to the left. There is also the application layer configuration file and application layer application file. The most important file among them is DAL cfg.h, and it is the file of the entire configuration DAL library. At present, the driver modules supported by DAL include the commonly used modules such as ADC, CAN, and CRC, and the special modules such as SPI and COMP. Next, we will introduce the DDL device driver layer. This layer provides the register-level underlying API interface, which has better execution efficiency, but poor portability, because the DDL library involves the configuration of more underlying registers. Therefore, you need to have a deep understanding of the MCU and its peripherals when using this library to develop applications. It is important to note that for the peripherals for which the execution efficiency is not a critical requirement or that require a higher-level protocol package, the DDL library does not provide the API interfaces. For example, SMC, DMC, and USB modules. The driver files of the DDL library are composed of the following files. Compared with the DAL library, its file composition is relatively simple. It has a bus.h file, which includes such functions as core bus control, peripheral clock enable and disable. The file of system.h mainly contains system-related operation functions. Cortex.h contains Cortex-M-related register operation API. Another type is public common API, which is included in the file of utils.c, and its pus.c.h file provides the peripheral initialization functions, such as the DDL ADC init function. The driver module of DDL includes the followings, and the commonly used are ADC, DAC, and DMA. Next, we will introduce the BSP. BSP will provide some API related to the corresponding demonstration board hardware, such as LED, buttons, LCD, SRAM, SDRAM, and other API related to the peripheral circuit. It consists of the following two parts, including BSP driver, which provides a set of basic API named according to the same naming rules, such as board, GLED, CONFLG, and board LED toggle. Another part is component. Here are some modules or chips, such as LAN 8720 and OV2640 driver component programs, which are decoupled from the API of APM32 MCU and can be ported to any demonstration board. The following table lists some common file names and their functions. The middleware consists of USB library, RTOS, file system, TCP/IP IP protocol stack, etc. The USB devices and host libraries include the following categories, and the operating systems are FreeRTOS and RT-Thread. The file system is FAT-FS, and the network protocol stack is LWIP. The SDK for the corresponding standard library of the DAL SDK in the application adds a series of source files and header files ending with CFG, and all of these files are used to configure peripherals and services. The file of device cfg.c.h will be used in a graphical generation tool that will be launched later. All the codes generated by this tool will be placed in this file, which contains initialization functions of DAL libraries, clocks, and peripherals. In addition to the above files, there are also configuration files of some libraries and some related configuration files of each peripheral service. There are also interrupt service functions and a main.ctoh, which is the user's application file. It mainly includes the function for calling the DAL device config, the callback of the user's peripheral interrupt, and the user's own application code. After introduction of the routine files, let's take a look at the directory structure of the entire routine files. As above mentioned, it includes the configuration files of peripherals, modules, configuration files of DAL library, device configuration source files, application header files, engineering files, application source files, and routine README files. If only the DDL library is used to develop applications, there will be no configuration files of the DAL library in the routine files. The SDK package will contain application routines of different demonstration boards. Below are a few tables, which represent the supported routine modules of each board. Let's take a quick look at them, and you just need to know where to find these routines. You can see the SDK README files for more detailed information. After understanding the overview of the SDK, let's take a look at how to quickly start and carry out testing and development work. The following chapters include how to run routines, how to develop DAL applications, and how to develop DDL application. The first is how to run routines. This section will introduce how to run a routine in the DAL SDK. Here, take the template routine as an example. First, download the APM32F4xx DAL SDK package from the technical support page of the GHI official website. Decompress it to the local directory, and then open the template routine directory. Our SDK package contains 3 different IDE projects. Here we need to choose one to open it, and you can choose your preferred toolchain. The following shows the import and operation process of each toolchain. Here we take MDK as an example. MDK needs to open the template in project ARJMDK directory, open its workspace, select the project menu, rebuild all target files menu, and recompile all files. Finally, select the Start-Stop Debug Session menu, download the application to the target MCU, and then go to the Debug Run menu to run the program. Then we can run the application routines in our SDK. IAR and Eclipse have the same process. Eclipse is slightly complex. It requires creating and importing the workspace first, and other processes are similar and will not be repeated here. After we know how to run routines, how to develop applications based on the DAL library. Here, I draw an application diagram and you can take a look. Our application codes include the DAL library, BSP, device config, configuration tools and middleware of GHI, as well as these parts supported by IDE. You can see which parts of codes form our entire DAL application. From the above picture, we know what files are included in the DAL application, but that's not enough. We still need to know the configuration model of DAL. From the following figure, we can see that our DAL driver model includes the interrupt service layer, application layer, device configuration layer, device driver layer, and service layer. After learning the above application and configuration model, how to develop DAL applications, below are the development steps. First, create a project. We can create an application project using a template project or any examples project. The template project provides a set of empty APM32 FilePy cfg.c.h configuration files and functions, and has a main file of while loop. Users can configure peripherals and write applications in this project. The entire template project includes a DAL driver library, CMSIS, and BSP drivers. Note that this project enables all DAL modules, and users can modify it in the APM32F4xx DAL cfg.h file. Moreover, it includes correct predefinition of library, BSP, and MCU models. In the configuration file, a DAL library is initialized, the system clock is configured to the maximum frequency of the device, and it also has a DAL delay function implemented with SysTick timer. When users do projects based on this project, it can facilitate users to carry out the subsequent application development to the greatest extent. Then, add the driver components. Users can add the components provided by SDK in the board or components directory to implement drivers for onboard peripherals. For example, if the user uses the Tiny development board and wants to provide driver support for its onboard LAN 8720 chip, he can choose the driver component file in the SDK package. Then add the middleware. Such middleware as APM32 USB library FATF FreeRTOS, RT thread, and LWIP can be used. How to add the source files of each middleware to the project. This requires referring to the help files of various middleware, or referring to the routines for the use of middleware provided in the SDK. Then configure the DAL library. The configuration items of DAL are in the file .dalcfg.h, which is included in each routine. In the include directory of the library, there is also a template file, and users can copy it to their own application project and customize the DAL library configuration. The main configuration content includes: firstly, enable of assertion. Secondly, enable of log components. Thirdly, enable of DAL module. Fourthly, configuration of clock, crystal, oscillator-related parameters. Fifthly, MCU system parameter configuration. There is also the callback function registration enable and ETH-related parameter configuration. Next, configure the system clock. In the device .cfg.c file of the template project or routine, there will be a default system clock configuration function, and the system clock will be configured by default as the maximum frequency of the device, mainly using the following two API. Users still need to write functions based on their own clock input and clock frequency usage. Sixthly, initialize the peripherals or modules and write the device config function, which can be configured according to our predefined function template or be implemented separately by yourself. Here, it is recommended to initialize the peripherals in the following order, including the following points. Finally, call the config function of each peripheral after the config peripheral ta comment in the device config function. Of course, users can also initialize in the main function by themselves. Finally, develop the client's own application. After a series of previous configurations, the system's peripherals modules have completed initialization. Users can use the polling, interrupt, and DMA API provided in the DAL library to process business codes or implement relevant processing logic on their own. It is important to note that in some application development, sysdic may be occupied, which may lead to changes in the actual time base of DAL. At this time, a timer can be used to provide a clock for DAL. There will be a template file in the source directory of the driver, and users can refer to it for implementation. The SDK provides a DAL library, as well as a DDL library. Here, let's see how to use it to develop the DDL application. First, create your own application project based on the template DDL project. This project will provide the files and functions with basic configurations and the main file of while loop. Users can configure their peripherals and write applications in this project. It also includes the DDL driver library, CMSIS driver, and correct driver library file and MCU model. At the same time, in its configuration file, the system clock has been configured to the maximum frequency of the device, and sysdic timer flag is initialized to implement the DDL mDelay function. Next, configure the system clock. There will be a default configuration function in the device config function in the template project or routine. Inside, the system clocks needs to be configured in a certain order. First, enable the external internal oscillators, wait for the oscillators to be ready, then configure the flash cycle, configure PLL, configure AHB frequency division and system clock source, configure APB frequency division, and finally update the system core clock variable. After completing the system clock configuration, the peripherals modules need to be initialized. Like the DAL library, a default DDL device config function is also provided here, and the clients can configure according to the predetermined function template or implement it by themselves. Conduct peripheral initialization in the following order. Enable the peripheral clock, configure the corresponding GPIO of the peripheral, configure DMA and enable DMA interrupts, and enable the peripheral interrupt. Handle the peripheral or DMA interrupt in the interrupt service function file, and call the DDL device config function in the main function. Finally, develop your own application. After a series of previous configurations, the peripherals modules of the system have completed all initialization, while the DDL library only provides an API close to the lower layer. Therefore, users need to implement the related processing logic of peripherals, such as polling, interrupt, and DMA on their own. The whole introduction is over, and thank you for watching. Welcome to follow the G High Media account to get more information. Thank you.